Here we go. On your drawing, draw two shapes there. One that represents the area from 0 to x. The other one represents the area from 0 to x plus h. We will use this diagram as a representation for understanding exactly the fundamental theorem of calculus. Now, what I do for you today is not a sufficient proof, but it is, as I would say, a brief reasoning behind the fundamental theorem of calculus. This is something that we can all understand, and we can take each other through, and you'll see why this works out, which is pretty nice. So I'm going to write something up here, and it's similar to what I wrote on the board yesterday, and it's namely that if I want to focus on this shaded area right here, okay? And that shaded area is the integral from x to x plus h of f of x dx. Yes? So yesterday I gave some of you guys harder problems that had a different beginning point than just 0. And so what we can do is we can define our interval by simply placing it there. And then what we can do is we can subtract the two integrals. Basically, if I took the area from 0 to x plus h and subtracted off the area from 0 to x, I would be left with that increment there. So I'm going to write that on the board. Notice if I take, again, the area of the big portion minus the area of the smaller portion, I get this leftover region right there. And so I'm going to write an expression for that. Namely that the integral from 0 to x plus h of f of x dx minus the integral from 0 to x of f of x dx. Every step in this process is extremely important. Unfortunately, we can't just say, okay, we need a zone in here for 1 minute and understand this piece. So first of all, I'm going to stop each time. Everybody get that? Okay. Now I'm going to write something else on the board that looks kind of odd, okay? F of x times h. This is where the magic kind of happens. We got to understand this argument. Can somebody tell me what does h represent up there in my drawing? The width. Yeah, this width right here is h, right? This width is h. And if I took the function evaluated at x and multiplied it by that width, describe to me what I would get. I took the function evaluated at x, where's that? Up here. And if I multiply that by h, what would I get? I would get that rectangle. Yeah, like a left-handed rectangle. So if I did all that, I'd get this shape here, okay? If I evaluate it by x and I multiply by h, I get that shape. Okay? Is that a decent approximation for that area? Yeah. It's lacking. It's so inferior to what we did yesterday. So inferior. Okay? Well, how about this? What if I write this, okay? What if I say that area, f of x times h, I'm going to use this equal sign loosely for a second here, is actually equal to this area, this approximation, which Ashley said was a poor approximation. I agree. Well, I'm going to make it a really good approximation here in a second. So again, I'm saying that area in red that we just talked about, Ashley said that's a poor approximation, is actually equal to the area that we want to find. But here's how I'm going to make it a better approximation. If I move this point, x plus h, closer to x, true or false, the area would be, or this would, that would be a better approximation. Yeah, would you guys all agree if I took this and drug this closer, that, you know, eventually this that rectangle would become a very, very good approximation. And and as you guys know, we're not limited in how close we can drag it. I mean, we can approach zero, as close as we want. So I can make these two expressions basically equal if I just do this. If I take the limit as h approaches 0 for both of them, this isn't technically correct the way I have it written. It would have to be on both sides. But, that limit would have to go on both sides. As h approaches 0, I would definitely come up with a better approximation. I'm going to do something here, and don't freak out. Okay, yes. The area I'm trying to find, you say that the red rectangle is a bad approximation right now. But if I move x plus h closer, then the new rectangle that I would draw would be a much better approximation. And if I draw extremely, extremely close, they're going to be darn near identical, aren't they? So I would say h is approaching 0. The width is approaching 0. The distance that they are apart is approaching 0. Yes? Okay, now I need to insert something. See this x plus h to x? That's up here. I'm going to insert this piece right here back in for this down here. And the aha moment is coming very quickly. F of x times h is approximately equal to the limit as h approaches 0 of the integral from x plus h to 0 of f of x dx minus the integral from x to 0 of f of x dx. So I just substituted something in. And now I'm going to do one last thing. I'll leave it. I'll let you look at it. I'm not going to. I'm going to tell you that the aha moment should be now, but it's going to occur at different points for you guys. Okay, it's going to occur at different points. See if you can figure out why this is interesting. I'm going to get rid of this h, and I have f of x is equal to the limit as h goes to 0 of the integral from x plus h to 0 of f of x dx minus the integral from x to 0 of f of x dx all over h. Ah! I saw it. Bryce, say what you just said. That's that. Okay, so Bryce has recognized something. He said that this is that. Back there on the wall, f of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. He says that these are basically identical. Look. Yes, it does. Yes, it does. Don't ruin it. You're ruining it. Look, in the first part, it's f of x plus h. Look, you're x plus h. Yes. So Ashley is 100% correct that there is something odd about this compared to what we see, but there is also something very unique. They are in some ways, and here's what we know, okay? True or false? I mean, this definite integral, we've used this to represent area, right? So this is like an area function. And this limit as h approaches 0, that is a derivative. So somehow the area and the function are somehow related through a derivative process, namely this. And this is how it works. A statement about f of x. Thus, f of x is equal to the derivative of the area function, or the integral. But we're not concerned about that necessarily. We're wondering what is the relationship between the area function and f of x. I've kind of written it backwards. It says f of x is the derivative of the area function. Well, if we know that's true, then we know this is true. The area function, or the integral, the area function or the integral is equal to the antiderivative of f of x. We haven't defined antiderivative yet, but we will. It's not real hard, but the nice thing is about any function, we can find the derivative of it. We can't find the antiderivative of everything. We're somewhat limited. But we can find antiderivatives and evaluate these areas over here that we talked about extremely quickly. You guys are going to see it right on our back page. And so this is the fundamental theorem of calculus part 1, which namely says this. Let f of x be continuous and differentiable. Over an interval a to b. This is notation that I choose to use. Your book does not. Large f of x is equal to the integral from x to a of f of x dx. Where big F of x is an antiderivative of f of x. So if we want to say what the derivative of f of x is, how do we represent that notation-wise? F prime of x, f double prime of x. We put that little comma up there. If we take an antiderivative of f, we call it large f. That's notation that I like. I think that students find easier to understand. And so here's really the idea. Here's an antiderivative. Let's suppose that you have f of x is equal to x to the n power. The antiderivative, well, one antiderivative, there's many. It doesn't really matter. You just need one of them. Large f of x is equal to x to the n plus 1. We increase the power by 1, and instead of multiplying it, we divide by it. Let me pause this. We increase the exponent by 1 and divide it by the new exponent. That's it. That's the antiderivative. Let's find an antiderivative. Summation. That's what we've been doing. We've been doing summation. Yes, different. F of x would be x to the 4th over 4. If you want to check to see if it's right, take the derivative. If you take the derivative of x to the 4th over 4, you'll get 4x to the 3rd over 4. And the 4's cancel, you get x to the 3rd. F of x is equal to 5x to the 5 over 5. And they cancel, so large f of x is equal to x to the 5th. That's the antiderivative. 4x to the 6th. What's this one? It will get harder, but, you know, this is the idea. Yeah. We're going to practice it while it's nice and easy. Yeah, this one's a little bit more difficult. I'm going to rewrite this one to be f of x is equal to 3 over 2 times x to the negative 3rd. So again, I increase the exponent by 1 to be 3 over 2 x to the negative 2, and then I divide it by what? My new exponent, which is negative 2. So divide by negative 2. So f of x would then be 3 over negative 4x squared. So you can see there's some that become difficult, but we can work through them. That brings us to Fundamental Theorem of Calculus Part 2. And here it is. The integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. That's it. That is it. And I'm going to pause. So if you recall yesterday, actually on Tuesday, we started with this very large problem, which was A. We said, what is the area from 0 to 2 underneath the curve x squared dx? Remember, we set up 4 rectangles. We found a right-hand sum. In fact, we practiced a left-hand sum. We did a trapezoidal sum. And then we expressed all that stuff. And you remember what the final answer was? 8/3. Let's do it nice and quick. That is equal to, what's the antiderivative of x squared? X to the 3rd over 3. And here's the notation we write. We write a bar, 2 on top, 0 on bottom. That means we evaluate that at 2 and 0. What is x, or what is 2 to the 3rd? 8 over 3 minus, what is 0 to the 3rd? 0 over 3. You get 8 to the 3rd. Yep. It happens that fast. Well, you know, I need a reaction from you guys. I need a reaction. Again. Yeah, how might the others respond? I don't know. I hope there's not a letdown, but so we just need an antiderivative. What's the antiderivative? 3x squared. 3x to the 3rd over 3, which is x cubed evaluated at 4, 2. So as I work this out, 4 to the 3rd minus 2 to the 3rd, 64 minus 8 is 56. See, sometimes when I teach, I really have to think about what do I have to communicate to get them to understand it. But now, for the rest of today, it's kind of, you guys are going to get all of it, aren't you? I mean, it's easy now. Well, now we're starting to appreciate the fact that some of these are, might be more difficult to find antiderivatives for. Yeah, some of them are difficult to find antiderivatives for. Well, let's try this one right here. it looks like this could be the integral from 2 to 1 of 3 times x to the 1/2, correct? Dx. So all you guys know how to deal with right now are powers. But notice that, we have, I mean, come on, it's going to follow what it did from differential calculus. We have situations where you have a chain rule type operation, you have a product. So some of those can be a little bit trickier. But this, as long as we can rewrite it as a power, we're good to go. And so what is the antiderivative of that? 3x to the 3/2 over 3/2. Evaluated at 2 and 1. So if you take 3 and divide it by 3/2, you get 2. Right? 3 over 1 divided by 3 over 2, multiplied by the reciprocal, and you get 2 over 1. So this is actually equal to 2x to the 3 over 2 evaluated at 2 and at 1. Yes. Oh, good question. The question is what happened to the 3 there? Here's what happened to the 3. If f of x is equal to 3x squared, then large f of x is equal to 3x to the 3rd divided by 3. So that's all where it went. But yes, your constants do stay around. In fact, you guys, if you wanted to, you could actually move the constant outside it entirely and just work with the function and multiply back through at the end. So now I'm going to plug in 2 and I'm going to plug in 1. So what is 2 to the 3rd? 2 to the 3rd is 8. And then I take the square root of it. So the square root of 8. So 2 roots of 8. Minus, and then we plug in 1. What's 1 to the 3rd? 1. Square root of 1 is 1. So minus 2. 2 roots of 8. What is root of 8 factored or reduced down to? 2 roots of 2. So I'll have 4 roots of 2. It depends on what the problem asks for. You should be capable of showing its simplest radical form. If on the test it asks for a decimal, then you could do that. But I haven't looked through exactly what the book asks either. If it's plus or minus, integrals can be separated by sums and differences. No problem. Products and quotients is different, but sums still work out. We can just keep it all the same. So I'm going to take the antiderivative of, what's the antiderivative of x to the 3rd? X to the 4th over 4. Minus x to the 3rd over 3. Plus x squared minus, 3x. Because this is currently 3x to the 0. And if you increase that 0 to the 1st power, then you would be x to the 1st over 1. So if you see a constant, you would just add an x onto it. So minus 3x. And we're going to evaluate that at 1 and 0 and subtract the results. Well, it would be, I did the x squared as x to the 3rd over 3, 2x squared over 2. So I evaluate at 1, I would have 1/4 minus 1/3 plus 1 minus 3 minus the function evaluated at 0. What's the function evaluated at 0? 0. So I'm going to turn everything to fourths here. Or 12ths, excuse me. 3/12 minus 4/12 plus 12/12 minus 36/12. -1, +11, -25. Now, why is that answer interesting? What does that mean? What? Go ahead, say it. It can be negative. Take out your calculator. Let's plug this in. Let's graph it, see what we get. X to the third minus x squared plus 2x minus 3. And I'm simply going from 0 to 1. So I'm going to change my window just a little bit. And I'm going to have an x min of -1. And I'm going to go to positive 2. And that should be more than sufficient to see all the information I'm looking for. So, yeah, if you look at this, Luke, please. If you look at the shape right here, if we would go to this calculate piece and we go to calculate number 7, and the lower limit, again, is 0, the upper limit is 1. As you evaluate this, you can see that it's finding all the area happens to be what? Below the x-axis. Area below the x-axis is referred to as negative. Area above the x-axis in calculus is referred to as positive. And some people may say, how could area be negative? Well, that's a difficult expression. We do talk about net area, in which we'd say that would be positive as well as that, but we'll get to that at a later point. That involves a very big. Yes, I do. It's just we do not know near enough calculus to investigate that. Yes, you don't know what the antiderivative sign is. What is it? Negative cosine. Think about it. If you take the derivative of cosine, you get negative sine. So the antiderivative sign can't be cosine. Negative cosine. And if you need to check, you could try taking the derivative. The derivative of cosine is negative sine, and then make it negative again, so it's a positive sign. So we need to be able to go back and forth between those things. And trust me, guys, we'll spend a lot of time in this class figuring out antiderivatives, because some of them are really hard. A lot. So we need to evaluate this now. We go negative cosine of pi minus a negative cosine of 0. Okay. Well, what's the cosine of pi? -1. So -1 is 1. And if you don't believe me, then you could go to your calculator and make sure that you're working in radians and go cosine of pi, and you get -1. Minus a negative, so plus. What's the cosine of 0? 1. So the exact area bound beneath the curve sine of x from 0 to pi is exactly 2. I believe we showed that the other day, didn't we? We broke it up into 100 rectangles. You're supposed to do that in an assignment. And you came up with 1.99999 a little while ago. And so we try a last one. The integral from 5 to 1 of 2 over x squared. I need to rewrite this. How will you rewrite that? Yeah, the integral from 1 to 5 of 2x to the -2 dx. And so what we need to do is we need to increase by 1. And so that will be 2x to the -1 divided by -1. Evaluated from 5 to 1. Or I don't like the x to the -1 up there, so I will simply move it like this, a -2 over x evaluated from 5 to 1. Those expressions are the same, so we have to be able to move our exponents around. Now that we have 5 and 1, we plug it in. I would have -2 over 5 minus a negative 2 over 1. Plus, there's negative 2 over 5 plus 10 over 5, which is equal to 8 over 5. The exact area founded within seconds. That is the fundamental theorem of calculus. I want you guys to realize something, though.